Ladies and gentlemen, start your mathematical engines. Let's get going on lesson 6.5. Welcome CTM students and anybody else who might be watching a lesson about variation. So we're talking about variation. What is it? Why is it important? Why do we care? Variation, direct variation, inverse variation, and joint variation. What those three things mean. That's the major three things we're looking at here in this lesson. So let's get started. Let's get right into it. We are going to begin with a summary, actually. So the book goes through a little more depth, a little more detail in this, but we're just going to summarize everything here. So a summary of variations right up here towards the top. We can assume that we're going to have some letters representing things down in these equations. Assume that k is a constant. That just means it's a number that we can either know the value of or we can determine the value of based on numbers that will be given, but it's not a variable. It's going to be a constant term. It's not going to change from one value to the next depending on what the others are. The other variables are these variables. X, Y, and Z are going to be variables. These are things that are going to change or vary. That's why they're called variables with the equations, but the k, the constant term, will be the same. So X, Y, and Z are variables. So let's assume that that is true. We've got three different things: direct, indirect, I'm sorry, not indirect, inverse, and joint. So direct, inverse, and joint variation. Direct variation looks like this. You have y equals some number times an x value. So this number again is a constant term. It could be 2, it could be 3.6, it could be 1/2, it could be negative 18.6 repeating, something like that. But it's just a constant term. It's a term that's going to stay the same no matter what. X and y, though, are variables. They can change. So in this one, y increases as x increases. So as the values you plug in for x get bigger, that means you're going to get values here that are also going to get bigger. So y increases as x increases. For inverse variation, instead of multiplying, we are dividing. We're taking k and dividing it by x. So inverse, you're going to see a form like that. Y, in this case, as you plug in larger values for x, because you're dividing this constant term by x, the y values are going to then become smaller. So larger values for x makes smaller values for y. So in other words, y decreases as x increases this time. And then joint variation, it's kind of like you're joining things together. You're joining variables together. And so it looks something like this. This k, again, is just some number that we'll know the value of, and then the x and the z will be variables in this case. So this is what joint variation looks like. Really, this lesson, I think, is more about terminology and understanding the way they word things than anything else. If you start to catch on to how they word things and how the forms look, it's really, I think, a pretty straightforward lesson. We just have to make sure we understand what the forms look like and we understand how things are worded. So y is going to increase here as either one of these two values increase. So as either x or z increase. So these are the major things to know here: direct variation, inverse variation, and joint variation. And let's check out a few examples. I believe your book has 10 examples on this one. We're going to do a few together here. Not that many, but we'll do a few ourselves here. So here's example 1. Suppose y varies directly as x. This is the way they word the sentences in your book, so I'm going to do it the same way here so that we get used to that. But to me, it sounds a little funny. Grammatically, it sounds a little strange, but this is the way that is appropriate to say it, according to the book at least. So suppose y varies directly as x. To me, I feel like we could say as x does, or varies directly with x, I feel like would be another way, but potentially even a better way to say that, but we're going to go with this way so that we get used to how the book will word it. So y varies directly as x. And so as x gets bigger, since it's varying directly, y is going to get bigger. We go back to our direct variation, and that is the case. So we need to find the, here's a new phrase for you, constant of proportionality. Oh, what the heck is that? What does that stand for? That's the k part here. So the constant of proportionality, that's the constant part right here. So we're going to find that constant, what that has to be. And I'm going to underline this because this is a phrase you should know, part of your vocabulary for this lesson. Constant of proportionality k if y equals 40 when x equals 30. So since it's direct variation, let's circle that here, direct, and we're going to write down the direct variation equation. And so here, I want you to draw a little arrow here, that's where that came from. So we're saying it varies directly, therefore we're going to use this equation. And now we plug in the numbers we know and solve for what we don't. We know that y is 40 when x is 30. So if I plugged in 30 for x right here and 40 for y right here, that would do that for me. I'll use parentheses for right now. We could rewrite this as just 40 equals 30k. That's more how we're used to seeing that. And then different color for this point. Let's divide by 30 here. That'll do what I want to do. The 30 will cancel out with the 30 here. The 0 and 0 will cancel here. I'm left with 4/3 for my k value. Sometimes you'll have fractions, sometimes you'll have decimals, and that's okay. This happens to be a fraction for this one. So that means if you went back up to the normal, or the original equation, you would have y is always going to equal 4/3 times whatever x is. It's going to be 4/3 as big as x. And so that's our direct variation formula to find the constant of proportionality. Pretty straightforward there. Let's do one where it's a little more involved. So example 2, maybe this was you when you were little. You rode a tricycle and then you got older and you wanted to drive NASCAR. I don't know. A little difference in speed right there. Hey buddy, go across the driveway. Hey buddy, go 2 miles in 10 seconds or something like that. I think that's a little fast, but let's say, or we know this is true. I know that speed equals distance over time, or speed, another word for speed is rate. And if you think about that, that would mean that time is going to equal the distance you traveled divided by the rate you were going. So for instance, if you're going 100 miles per hour, or if you're going 100 miles at a rate of 50 miles per hour, that would take you 100 divided by 50 would be 2 hours. And so time is related in this way with distance and a rate. So hopefully you're noticing, this seems like an inverse variation right here. We've got this divided by part here. It's going to vary inversely. So time equals distance over rate. Since that's true, time varies inversely. And we could say with, we could say as blank does, but the book states it as rate. So that's just the same way as saying time varies inversely as rate does, sort of like that, or with rate. So as rate gets bigger, time gets smaller. As you go faster and faster, the time it takes to cover the same distance will get smaller and smaller. That should make sense, I hope. So if you have a distance of 100 miles to cover, or to travel, 100 miles to travel, find the time oops, the time it will take to travel this distance at both 50 miles per hour and 40 miles per hour. So we'll pretend this car is going 50 and you are flying on your tricycle at 40 miles per hour. Oh boy, I think that would be a lot scarier than going in a car 50 miles an hour. Oh my gosh, that would be crazy. Cray cray, that'd be crazy. Solution. What are we going to do? I'm going to split this into two parts. So I'm going to have over here at 50 miles per hour and over here at 40 miles per hour. I did already verbally say what the answer was here. I actually wasn't even thinking about this particular problem being 100 miles. That wasn't what I was going to do. I just kind of randomly came up with that number, and it seems I came up with the same number as I did before. So here, time equals distance over rate. So time equals, you can say T equals D over R as another way to say that in a shorthand way. And here we'd just be plugging in 100 for the distance and 50 for the rate. And so this is very straightforward. This time we don't need to solve for this constant of proportionality. We know the constant value, the distance is the constant value. Your K value here then is 100. No matter how fast you're going, the distance is still 100. The distance remains constant. And so here it would be 2. This is a time, miles per hour over, or miles over miles per hour. You would have 2 hours for your time right there. In your solution for 40 miles per hour, use the same formula, T equals D over R. That would mean you have 100 again, that's your constant term, and then you have 40, that's your varying term, the speed, the rate is changing. This then becomes, let's take out our different color to simplify things here. This would be crossing out here and here. You could reduce that down to 5 over 2. Now you're not going to tell somebody, yeah, I drove for 5 hours today. You're probably going to say 2.5, or you're going to say 2.5 hours. One of those two things. When you give an answer, it should make sense. It should be a reasonable way to state something. Again, you're not going to say, yeah, I was running today for 5 hours, and you're just going to get strange looks. Hopefully not because you're running, but because you gave your answer as an improper fraction in terms of time. Cray again, you're just going crazy today. I know, I'm going crazy today. Mr. Wagner is, he's always a little crazy, isn't he? Now that I'm talking about myself in the third person? Yeah. Suppose D varies inversely as C. So that wording again shows up like that. That just means D varies inversely as C. D is like your Y value, C is like your X value. Now you don't always have to use those letters, but as C gets bigger, that means D is going to get, since it's inversely, D is going to get smaller. So let's say that this is true. If D equals 7 when C equals 21, find D when C equals 13. And let's get out our different color here. I want to circle this word right here, inversely. So just like we had done here with the directly, we're going to start off with our general formula, our general equation for direct variation. Here, instead of here, it's going to be the general formula for inverse variation. So what's the inverse variation formula? It was this y equals k over x. I'll write it like that to start, but then we're going to replace the x with the c and the y with the d, because d is the one that's varying inversely as c. So this is your x value. This as part is your x value. The part that is varying with that is the y value. So this becomes now d equals k over c. So we can say that here. So, or here, it is D equals K over C. So we're going to plug in values now. I know that D is 7 when C is 21. So let's plug in 7 right here, and let's plug in 21 right here. I don't know my constant of proportionality yet. I don't know what K is. So I'm going to have to solve for K right here. So let's take out our different color, and to do that, we need to multiply both sides by the denominator I see there. Multiply both sides by 21. That will cancel out there and there. And that leaves me with my constant of proportionality. I know my K value then is 147. Now that's not my final answer, but that's a critical component needed to find my final answer. So since that is true, we can say this. Therefore, that D equals K over C can become, or it does become, becomes D equals, we've got now K as 147. That's the constant term. And your C, when C equals 13, it says. So that over 13. So let's take this, let's circle that part right here, and I'm saying that's where that came from right there. So that's where that 13 comes from. The 7 and 21, that's where that came from, here and here. And so now it's just a matter of typing that into a calculator. We could say that that's the value. It's 147 over 13. If you put that as a mixed number, let's see what that would give us. How many whole times does 13 go into 147? We'd have 11 whole times, and then we would have to do 11 times 13. That would give me what's left over, the remainder. So 11 times 13. It's 143. That's 4 less than 147. So you'd have this as another value, and then you could approximate that, which we had done. Let's retype that in. 147 divided by 13. That's 11.307. Let's go to 2 decimal places for now. 11.31 would be what that approximately is. So 3 different answers. This time there's no context to the problem, so improper is just as good as the mixed number or the rounded off decimal. Let's check out example 4 now. We're going to do a couple more here still. The area A, you may recognize this shape. It's not a kite. The kite's a little different. This is a rhombus. All 4 sides are the same, but not all 4 angles are necessarily right angles or 90-degree angles. So the area A of a rhombus varies jointly. Aha! We haven't done that one yet. So it varies jointly as its diagonals. That's the way it's phrased in the book, so we're doing that the same way here. I might say with the diagonals. So as the diagonals get bigger, as those values, this would be a diagonal right here. You don't have to draw this picture, but that would be a diagonal, and that would be the other diagonal. As these 2 things get bigger, or either one of them gets bigger, the area of the whole rhombus is also going to get bigger. So as its diagonals, and we're going to call those diagonals D sub 1 and D sub 2 for diagonal 1 and diagonal 2. So little subscripts right there. If the area of a rhombus is 36 centimeters squared, area is always going to be in units squared, by the way, when D1 equals 6 centimeters and D2 equals 12 centimeters, find the area of a rhombus with D1 equals 14 centimeters and D2 equals 20 centimeters. So let's go back to this joint variation formula. So it varies jointly. Let's circle that in our different color, and let's bring this down here to start with the the initial equation that we need. So our solution here, what's the joint variation look like again? It looks like this. Here we go, one more. So y equals k times x times z. And so just like before, we'll write it out just like it is there. So y equals k x z. But what are my variables? What are the things that are changing here? Well, it's my d1 and my d2. Those are the things it's varying jointly with or as its diagonals. So we're saying this we can write, or here it becomes that the area is varying jointly with the diagonal. So k, that's still our constant of proportionality. We still need to figure that out, but also d1 and d2. So k times d1 times d2. That's what it's looking like here. And so let's plug in those values that we actually know. We know that when area is 36 centimeters squared. I don't know what the constant proportionality is yet, but I know that when the area is 36, that means d1 is 6 and d2 is 12. That is a possible combination. So we can solve for k from there. Then we have the general formula that always works, and we can plug values back in there to solve for missing values from there. So we have k times, this is 72 right there, so 72k. Take out your different color, would show that, divide by 72, divide by 72. This would cancel out here and here. This would become 1/2. We can reduce that down to 1/2. So that's my constant in proportionality. That means, I'm going to continue this over here. You should have more room underneath yours probably, but I'm just going to finish it off over here so I have enough room to fit that in. So that means that A equals K times D1 times D2 becomes, for the other information we have, we can write that the area, which we don't know, would equal 1/2 times D1 is 14 times D2 is 20. And so here, we take half of 14, that's 7, and 7 times 20 is 140. So I have 140 centimeters squared for the area of the second rhombus right there. So I'll write that down there for the second rhombus. And you may recognize this formula, this A, the area equals 1/2 D1 times D2. That formula comes from geometry class. It's just half of each of the diagonals multiplied together. Why that is, the real quick intuitive way to think about it is you could make a rectangle like this. You don't have to draw this again, but you could make a rectangle like this that would go around the outside here, and the length of the rectangle would be the length of this diagonal right here times the length of this diagonal right here. So you'd have D1 times D2. And you're only taking, for each part here, each little triangle is half of the smaller rectangles that you see in here. And so the whole thing is half of the larger rectangle that you see here. The formula is based on that, so I didn't just make that up. That was coming from that. And finally, example 5. This is something that's a little new. You can actually combine these formulas together. So direct inverse joint, you could combine those things together. You could have joint inverse variation. You could have a joint indirect variation. There's different ways to combine these things together. So this last one is going to show us, or we're going to see some combined variations in this last one. So let's say that this is the case. Suppose A varies jointly as B and C. And inversely as the cube root. Maybe you forgot what that was from your algebra class, cube roots. So we'll talk about that here. We talk about it in geometry a little bit too, as the cube root of D. If A equals 6, when B equals 1, C equals 6, and D equals 27, This time we're going to just find the constant of proportionality again. So find the constant of proportionality k. Okay, so this one we have to combine two ideas together to start. It's varying jointly. Let's circle that part in our different color, and inversely. So if it's jointly and inversely, we have to translate this into an equation. What is that going to look like? So let's write that down, translating the first sentence into an equation it's going to yield this. It's going to yield that A, since A is varying jointly and inversely with these things, or as these things, we're having A, and it's varying jointly. So that's this part. That's K, constant of proportionality, times B times C. So let's take this right here and connect it to this part right here. So that goes with that. And it's varying inversely, so we have this divided by part in here. It's varying inversely with this part here. So I'm going to take this and go right there. And it's as the cube root of D. So the cube root of D, square root is just like this, but a cube root, how do we denote that? We have to write a 3 outside of there. If there's nothing written there, we assume that's like an invisible 2 for square root, but cube root, we'd put a 3 right there. So this inversely part we're dividing by, and then it's the cube root of D. So this then is going to become, or we could say therefore, let's plug in the values that we are given and find what k is from there. So we are given that A is 6. We are given that k is, we don't know. B, we know is 1 though, and C, we know is 6. And D, we know when all these things, all these values are like they are, that D is supposed to be 27. And so this then is going to become, let's not write it like that, let's continue the equation down here. This will be 6 equals, this will be 6k on the top. And then on the bottom, what number times itself 3 times equals 27? That's another way to say the cube root of something. What number times itself 3 times is 27? Well, 3 times 3 times 3 is 27. Therefore, the cube root of 27 is 3. On your calculator, fancy way to do that, or the way to do that, would be, let's see if I've got it here. I can raise something to, instead of the cube root, I don't think I have a cube root button. Actually, I do right here. So you can, if your calculator has this button, you can just hit that, and boom, that does a cube root right for you. You can also do 27, and you can raise it to a power. So I can, this is my power button. Some of you have a little caret instead. It'll just look like that instead. But if we take this to the, and I'm going to put 1/3 in parentheses, so 1 divided by 3. If I take that to the 1/3 power, that's what 1/3 is. I put equals, that gives me 3. That's another way to do that. And so from here, I'm running out of space, so I'll continue this over here. I could reduce that right there. I could have also multiplied by 3 and reduced later, but this I could say is a 2, and this is a 1. Therefore, I've got 6 equals 2k. And then finally, I can divide both sides by 2, here and here. That'll get rid of that, there and there. And that gives me my constant proportionality for this one should be k equals 3. And that'll do it for this lesson. Go back, and also, as always, go back to your books as well, or look in your books. Check out some extra examples in there. If some of these weren't making complete sense to you, there's 10 more in the book. We did 5 here. I tried to hit every little variation that I could in here. Try to do a little bit with joint variation, a little bit with inverse, and a little bit with combined, and a little bit with direct. So you saw a little bit of everything in here. Go check out the book and go review the video as needed to check out some more. Alright, hope you have a good day, and I will see you later.